Good morning or good afternoon, depending on where you are at, and very warm welcome to our monthly webinar at ABC UTC. My name is Atarut Azizi Namini, Director of the ABC UTC here at Florida International University. We are very pleased to let you know that the conference program for the 2021 Virtual Accelerated Bridge Construction Conference is now available. You can go to our website and view the conference program. The conference will be during the December 8, 9, 10, 2021. And during the December 9 and 10, we are also going to have a hybrid workshop on the UHPC. So just a couple of things. We would like to ask you, if you are enjoying to listen to these monthly webinars and you plan to attend this virtual conference, please register early. That will assist us greatly. And you can go to our website and register. Just to give you an idea, we are not going to, of course, go through the conference program, but the conference program includes all the information that you need from the exhibiting, from the information about every presentation. There will be 16 keynote talks. We will have 2 congressmen and a representative of the US DOT to be with us, share their thoughts. In addition to the keynote talks, we also have 30 presentations. There will be only one presentation at a time, so you will be able to listen to all the presentation. The recording of the presentation will not be put on our website. So the recording of the presentations will not be placed on our website. So if you like to see this presentation, please register and participate in the conference. The conference program gives you all the details. It starts on Wednesday morning, several presentation, keynote talks, proceed with the Wednesday afternoon, and then Wednesday evening we're going to have a reception. As you see, the presentations are coming from many countries in the world: Sweden, China, Switzerland, Australia, South Korea, and Spain, Canada. So there will be lots of good presentation. Very great opportunity to see what the rest of the world is doing in the ABC area. There will also be allocated time for the exhibitors to actually give a very short presentation, and some very interesting entertainment, which will be the world of the music, basically music from the around the world. So it's going to be a very interesting conference. So we really encourage you to register and register early to help us, and don't miss this opportunity. Friday again, we'll start every day, start at 9 o'clock, finish around 5 o'clock. The workshop is going to be starting from the 4:30, and then it will go actually until the 8 on the UHPC. The conference program includes the description of all the presentation, the very short abstract of all the presentation that you will hear. So there's an opportunity to exhibit and be a sponsor. These are the companies that have sponsored to date. And then, like I said, there will be a hybrid UHPC workshop, where part of the workshop actually you will see physically what does it feel like to mix ultra-high performance concrete. You will hear from several universities that have been active in this area, share their thoughts, and hopefully by all this, it's going to be basically fairly easy for you to make the UHPC in your own state using the ready-mix companies. We also have, in 2022, we are going to have a face-to-face conference in Miami, Florida. This December 21 is focused on the international, it's a virtual. So it's not the material that will be presented this year will be completely different than the material that will be presented in the 22. So we have decided to send a call for abstract from now for the 2022 ABC conference, And if you look at our conference program, there is a link that you can start to actually submit your abstract from now. Again, please register early by visiting our website. The early registration will greatly help us to better organize the conference.
Our presentation today features Montana's ABC Clark Fork River Bridge near Trout Creek Rehabilitation Project. We're pleased to welcome our presenters, Stephanie Brandenberger, State Bridge Engineer with the Montana Department of Transportation, and Lenci Kappes, Innovations and Complex Structures Engineer, also with the Montana Department of Transportation. Stephanie?
Well, thank you for the introduction, Mary Lou. Hello, everyone. We're very pleased to be here to share Montana DOT's experiences with this accelerated bridge construction project we call the Clark Fork River Bridge Rehab at Trout Creek. And I have the honor of introducing a few members of the project team who are on today's panel. First of all, Lenci Kappes, MDT's Innovations and Complex Structures Engineer, who was part of the pre-construction team and provided CE services during construction of the project, and he will be presenting the details of the project today. We have Bethany Kappes, MDT's Alternative Contracts Engineer and Bridge Construction Reviewer, who was instrumental in developing the alternative contracting guidelines that were an important element of this project, and we'll be discussing that today. And Ryan Paulson, MDT's Construction Project Manager, who is responsible for contract management and compliance. Dustin Hyros with HDR, the engineer of record for the Bridge Rehabilitation Project. So welcome, panel. Before we talk about our featured bridge project, I wanted to briefly discuss how and why accelerated bridge construction is used by Montana DOT. So our choice to use ABC is not always associated with high traffic volumes. ADT is relatively low in most areas of Montana, but the detours associated with taking a bridge out of service can quite often be hundreds of miles. Even small bridges out of service can have big impacts on commerce and communities. At MDT, we continue to develop our ABC bridge replacement details for small bridges, utilizing precast and pre-stressed decked girders and precast cap elements like those shown on the left side of the screen. We also have fairly short construction windows in Montana affected by the weather, where we can have freezing temperatures and snow into June and as early as October, like we have right now. We have numerous environmental constraints, timing restrictions in rivers to protect aquatic species, and seasonal traffic demands for everything from tourism to agriculture. These sites can often be remote, with access to construction materials somewhat limited, and we've utilized bridge slides to help us work around some of those challenges, like the bridge in the upper right corner of the screen, recently completed over the Judith River in central Montana. And when we think about ABC solutions, we might not always think about using it for bridge rehabilitation, but rehabilitation of bridges can have the same challenges as replacements, primarily related to construction duration and maintenance of traffic. And construction of the deck is often one of the longest duration activities on a schedule. So utilizing precast deck elements can reduce the overall project time significantly. And we're going to discuss how we use precast deck elements on our featured bridge rehabilitation project today. So Montana is a geographically large state with a small population and a proportionally small budget for the maintenance, preservation, and capital improvements of nearly 5,000 bridges across the state. Our featured project is located in the mountainous northwest corner of Montana, where there are fairly high levels of precipitation and freezing temperatures for several months each year. The bridge spans the Clark Fork River at the head of the Noxton Reservoir near the small community of Trout Creek. The bridge carries Montana 200, which is an east-west state primary route. It's on the National Freight Network, and it's used for multi-state travel and shipping. It's also regionally important to the community for school bus routes and other public services. So the essential purpose of the project was to rehabilitate the bridge. And rehabilitation was chosen to improve the overall bridge condition, particularly the deck, which was in poor condition, and to extend the serviceable life of the bridge. The deck had significant delamination throughout the entire surface and high chloride concentration, which had penetrated deep into the slab due to the frequent application of anti-icing chemicals. Because much of the structural section of the deck would need to be removed in order to eliminate the chlorides and prevent further corrosion, a deck replacement was chosen rather than a surface treatment like a partial depth mill and overlay. Complete replacement of the entire structure was not financially feasible for MDT, and we believe we could get several decades more functional life from the structure with a new deck and a rehabilitated superstructure. There were a number of significant challenges at the site. The bridge was originally constructed over the Clark Fork River in 1958 prior to construction of the Noxton Dam and creation of the reservoir. The dam is used for regional power generation, and a transmission line is suspended above the bridge. The main spans are composed of a two-girder, non-redundant structural system with a 28-foot wide deck, which limited phase construction options for our deck replacement. And closure of this bridge would affect traffic in Montana, Idaho, and Washington. So maintenance of traffic decisions for the project were a critical part of the early planning and development. And as we started evaluating the various site constraints, we realized that the contractor's means and methods would play a pivotal role in the design of the deck replacement itself. So the project utilized an alternative contracting method that allowed us to coordinate early with the contractor, which was an important part of the success of this ABC project. We ultimately selected full-width precast deck panels as the ABC technique to replace the deck, and the contractor came up with some innovative solutions to place them. We allowed a very short 6-week window to close the bridge and disrupt Highway 200 traffic, and that came with a very robust public information effort. The panels were fabricated locally in Kalispell, which is about 125 miles from the project site. And I think it's also important to mention that the contractor received the notice to proceed and began mobilizing to the site early in 2020 when COVID started shutting things down in March. I believe that the partnership developed with the alternative contracting and the use of ABC methods allowed us to press on with the project, mitigate risks and delays, and keep the project running safely. And I wanted to touch briefly on the alternative contracting method we used and what it meant to the project. MDT had just been granted approval by the state legislature to utilize this contracting method that we call Contractor General Contractor, or CMGC, which would allow us to bring a contractor, the construction manager, on board during the pre-construction phase. And we thought this project presented an excellent opportunity to test the contracting method on a problem that could really benefit from early contractor involvement. The project CMGC team consisted of MDT, the owner, HDR, the engineer, and Kiewit, the contractor, forming what we called the three-legged stool, each leg having an equal role that supported this project throughout pre-construction and construction phases. And Kiewit was ultimately awarded the construction contract, thus becoming the general contractor. So the pre-construction timeline for the project lasted just 9 months from project kickoff to contract award. Why so short? Well, funding for the project was available in fiscal year 2020, but it took some time to receive approval to use the new CMGC contracting method and get it through the RFP process for team selection. And we wanted to let the contract in December so the contractor would have time to order and begin deck panel fabrication, which was a critical path construction element. And we wanted to get the bridge rehab work done before more deterioration occurred. So that left us with a very narrow window of opportunity, but the team decided to take on that challenge and managed to meet this very tight timeline. So the majority of construction occurred in the summer of 2020, with full closure beginning in June and lasting just 6 weeks, where most of the deck replacement work happened. That closure window was selected based on stakeholder and community input to avoid these important events you see on the timeline. Traditional cast-in-place deck replacement would have taken at least twice that long, pushing the construction closure into September. Other construction activities did take place before and after that closure window, with minimal impact to traffic. So now, focusing on the interesting details of the ABC deck replacement for the project, I'd like to hand the presentation over to Lenci Kappes.
Thank you, Stephanie. You set us up perfectly to navigate through a few of the exciting details of this project. And to do just that, I've put together somewhat of a project itinerary, a little road trip, if you will. And so I first wanted to start with exploring more of the details of the project site. I also wanted to take a little side detour down memory lane with a project summary. And of course, I think we need to navigate through that 6-week closure when we close down MT 200. And then I wanted to do a little backseat driving and discuss the ABC deck panels. They're a huge part of this project. The ABC portion doing all that work in 6 weeks, and we're gonna just walk right through from design, fabrication, and then into construction. Of course, that puts us into the final stretch of our road trip, if you will, of talking about our challenges and then, of course, some lessons learned. And of course, are we there yet for some questions? I wanted to add that I've put the road trip itinerary down at the bottom of each slide, and so that'll help you keep track with your questions as well as maybe the slide numbers. To begin with, this picture shows the Clark Fork River Bridge over the Noxton Reservoir, and you can see the 920 feet of steel spans crossing the waterway as well as the Bonneville power transmission line in the distance. But really, it's what's hidden in the depths of this pristine waterway that really makes this bridge somewhat unique in Montana. Let's explore a little bit more on this pier beneath the surface. And so we can look at the bridge in the as-built, and we see that back when the original bridge builders were here, the reservoir was much lower. In fact, it was at this line. And so from the new water level to the bottom of that footing is 149 feet. And so when they raised that reservoir, it raised 116 feet. This makes the bridge replacement and bridge detours much more costly in the current state of the reservoir. Bringing us back to the bridge itself, the project team was originally planning to facilitate traffic on the bridge during construction. Well, there are many cases where bridge decks can be replaced while simultaneously maintaining that traffic. The Trout Creek Bridge was very narrow and it was made up of a 2-girder riveted system that really made one lane at a time with traffic, made that construction unsafe. And so based on a detailed structural analysis, the project team determined that the bridge may not adequately support highway traffic during deck replacement work. Therefore, the team, as we mentioned before, we did transition to requiring a full closure of the highway to complete the work. And again, safety was the primary driver of this decision, but also things like differential deflections of the bridge system due to live load traffic during construction were really a concern for joint cures and that overall quality that we wanted at the end of the project. Stepping back a little bit, I wanted to talk about some of the main features at the project site. I wanted to take advantage of some fantastic footage that we have to provide a better overview of the site and some of the work that we'll be discussing today. And this is in our itinerary, that trip down memory lane, but it's also kind of a project summary, so keep that in mind. We start out with a view of the Clark Fork River Bridge near Trout Creek, as we've seen before. Even though the bridge was around 60 years old, it has been well maintained and proved worthy of rehabilitation. And due to the site constraints previously discussed, including the extreme depth of the intersecting waterway, construction of a temporary bridge, either traditional or floating, was determined to be impractical and very costly. And while the project cost was approximately $10.5 million, it was estimated that a replacement structure would cost nearly 2 to 3 times that amount. So after much review of the structure and considerable design work, a plan was formulated to temporarily close the structure, remove the deck, and replace with full-width deck panels. So as shown, a temporary scaffolding was constructed beneath the bridge to provide safe access for the rehabilitation work, as well as contain a lot of the construction debris. Much of the work during the closure would be to remove and replace the deck panels. This was a delicate balancing act between large ABC components, construction equipment, and the structural limitations of the bridge itself. And so as you can see, the CMGC team that Stephanie talked about provided the innovation, that attention to detail, the technical expertise, the construction experience, and they compiled all this into a unique and creative solution, and all in a very narrow construction window. And that brings me to wanting to talk a little bit more about our pre-construction and that CMGC process. So I'm going to reuse this timeline. And while the team originally intended to keep the facility open to traffic, it soon became apparent that a closure was the safest and most cost-effective way to move the project forward. So therefore, in the condensed project design phase, several stakeholder meetings were held to provide a construction solution that made sense for the community of Trout Creek and the region. And the decision was made to condense the majority of the critical construction work into that 6-week full closure that we mentioned. When we look at a timeline of the construction activities, the 6-week closure really makes sense. Note that the 6-week closure is carefully bracketed in June and the first half of July, and this wasn't just for the sunny weather that we've seen in the pictures. Working closely with the community, the design team found a window that really minimized that public impact. And it's worth noting at this point that the design team also carried 2 closure proposals forward to the public, with the second option consisting of 12 weeks of intermittent closures. The additional cost of this option was estimated to be $2.5 million, and the option also overlapped with several important events on this timeline, like school, for example, and running those school buses. The 6-week closure, as shown, was obviously the choice selected. And we have to do a little more navigation through that closure. I don't think we can mention closing down MT200 without that. And so the only local detour for MT200 is what we call Blue Slide Road, and that's represented by this black line, 472. And Blue Slide Road, as its name might suggest, is a lengthy, narrow, and windy local detour route, and it's also load restricted. So to help mitigate the impacts of the full bridge closure, the bridge team helped coordinate access plans for emergency services. We collaborated with the trucking industry to notify carriers of applicable restrictions. They provided much needed safety improvements to Blue Slide Road that was of course used as just a local detour only during the construction. And we even facilitated a temporary dump site to make garbage disposal for residents more convenient, and installed hundreds of temporary mailboxes to reduce the travel distance for residents to access their mail. So as shown on the right, on the map on the right, this effort included a regional alternate route plan with single-use signs placed in Montana, Washington, Idaho. For example, we see Spokane, Washington. There's one in Coeur d'Alene and Sandpoint, Idaho. Basically, any route that led to MT200 was marked. And this was, of course, in addition to radio announcements and all forms of social media, mapping, etc. We didn't take the 6-week closure of MT200 lightly at all. And now, a little backseat driving. Let's talk about one of the big ABC components, and that's these deck panels. They represent the majority of the work completed during the 6-week closure window. And I think it still amazes me thinking back that in this remote part of our state, we're able to close a 1,000-foot-long bridge for only 6 weeks, completely remove the deck and replace it. I think these deck panels are a great example of accelerated bridge construction and really the key to bringing the success to this project. They are the result of an awesome design effort. It really combined the fabrication skill and the construction know-how. And we're going to be talking a lot about that. We're going to talk about formless joint panels. We required a mock-up. There's a cart and buggy system for panel transport, and even the crane movement itself I considered pretty innovational. So let's get some bookkeeping stuff done though. I wanted to mention for new bridge items, the design was prepared with the 8th edition AASHTO LRFD bridge design specifications and for HL93 loading. Also, you'll see what looks like some common black bars in the deck panel pictures that are coming, but we actually utilized Mmfx corrosion resistant steel in the deck panels as we wanted that additional level of corrosion resistance for this design. And a specialized but conventional concrete mix was used in the joints. The team did look into UHPC for this project, but ultimately decided the conventional concrete, it provided more flexibility for the contractor with the mix design and placement, given the requirements of the project. Additionally, there was a steel fiber shortage throughout the country at the time in 2019 when we were in pre-construction, and that added a little bit of risk to our project. Furthermore, the project team also determined that a more traditional but specialized joint concrete would save over $500,000 in overall project costs when compared to UHPC. And then speaking of cost, it's worth mentioning the total rehabilitation cost was $10.5 million. And then furthermore, the deck panels made up about $3.5 million of that cost. So jumping right into the design, I have shown here a typical transverse section of the full width panel. And the widened roadway width is 32 feet from that 28. And then with the curbs, these panels are actually 34 feet, 4 inches wide. The panel thickness is only 6.5 inches. And note that the curbs were chosen to be cast in place later. So they're shown here, but they're actually dotted, and only the steel for that curb is there. And that was to save weight and also to eliminate those longitudinal joints or those transverse joints in the curb. These full width panels still weighed around 25,000 pounds. We're now looking at another transverse section, but this time it includes the superstructure. There's an 1.5 inch overlay, so that'll make a total 8-inch deck thickness. There are shear studs on the main girders, and those are intended to make fully composite between the deck panels and those riveted main girders. And there's also shear studs on the stringers shown in this detail, but it's important to note those were only to provide lateral bracing for those stringers, not for composite action. And one note, we did a lot to reduce the weight, like the curb and rail will be added later, but the 1.5 inch overlay also was meant to provide a better riding surface continuity between all those panels. So here's a plan view of that same panel, and the panels were 9 foot 6 inches wide, and meaning, and that's just important to note out, I think for 920 feet of steel girders, that would be just under 100 panels to complete in that short construction time frame between January and April, May when we're out there. So I also wanted to point out, noting the blockouts for those shear studs, And then there's some leveling devices. The 2 concentric circles shown on this view are leveling devices. We had those on the main girders and the stringers as well. And then you'll see also some grout locations, so we can provide that haunch material in between the deck panels and those stringers as well. So a lot of details in here, and I wanted to go one step further and not to put this up to show all the steel in each little piece, but to show more the congestion. You know, there's a lot going on in these panels. I thought the design team did an excellent job fitting in all the required steel for structural purposes and detailing that out such that it could be built, and fitting around all these leveling devices and the necessary shear stud pockets and many other things. There's scuppers in some of the other panels that they did just a great job working all the details out there. Then something else that we did that was very innovative is we provided a formless joint at each panel edge. And so you'll see basically a tongue coming off of that panel. And here you'll see that same tongue, but with 2 panels together. And then you'll see all that continuous reinforcement that we're going to add to this joint to really shore up the connection between those 2 elements. And so we're going to be following this formless joint into fabrication, and then of course out onto the bridge during construction. So I think we have a great design, but now we have to build the gosh darn thing. So here we are, and we're in a Glacier Precast in Kalispell, Montana. And in the first picture on the left, you're going to see that they're just starting to place the concrete, but this is an excellent opportunity to see the blockouts for the shear studs. We're also going to see blockouts for the grout locations and then the leveling devices that we talked about earlier. Again, all the black steel here is actually Mmfx, and then you'll see some epoxy steel for the curbs. In the middle picture, you'll see that the placement of the concrete's further along. They're about halfway. You can see a screed board moving across. And then in the final picture, you'll see that they just got done roughening that surface and had pulling the side forms off. So these are, I want to mention at this point that these are our mock-up panels. We chose the first 2 for this purpose. And so we're evaluating a lot of things. We're making sure that we have the appropriate surface roughness. We want to make sure that our leveling devices work. You can even see that we have a nice roughened surface inside those shear stud blockouts. And of course, we're going to be paying special attention to that formless joint that we utilized on this project, which you see in the picture on the right. And we wanted to use these mock-ups and really push everything we could with these. So we put them on the trucks. You know, these are 34-foot long panels, 10 feet wide, only 6.5 inches deep. So we want to make sure when we're handling them, when we're driving around, that we're not cracking those more than what we had, anticipated. And so we're doing a lot with these panels. And then of course, one of the most important things that we could have done in the start was to make sure that we could fit all that joint steel that was really going to shore up, that joint for the design and make sure it was actually working out before we built the other 96 of these panels. There's smaller things like that we learned on the mock-up, like you can see the edge on the picture on the right that I'm pointing at with my mouse. You can see that there's some slight cracking and it's sloughed off a little bit. Well, the Glacier Precast immediately recognized that they pulled that form off a little bit, and then of course, adjusted their processes so that didn't happen again, and we had nice clean edges. So we really did learn a lot. In this picture also, this is as far as we can push those transverse bars. So we did recognize a clearance issue that then of course that sends us right back into the shop. And so, this is an important lesson learned, and Glacier Precast did a great job. They jumped right in there and they did some modifications to their connecting form work right there. And then in the middle picture, you also see that they just put some simple wedges in to help ensure that they had that clearance that we required, or that the design required. And then here, of course, they're finishing another panel. And this time we're viewing it kind of from behind that screed board from the finished side. And I put this blurry picture in to show the connectivity between the design team, the fabricator, the contractor, and MDT. This team was moving fast to get these panels made. You know, prior to closing the bridge, we only had a few months, and Glacier Precast in that few months needed to make 98 panels and have them shipped to the project site. And so this blurry shot really represents a lot to us. And it isn't just a bribe, but I think it's rather a quick picture that satisfied all the concerns that the new changes created or corrected the necessary clearance that we had needed in those formless joints. So that was kind of our money shot, and just meant a lot to us. And we're of course going to follow those panels out to Trout Creek. And so you'll see that the contractor, Kiewit, has done a great job of simulating what those panels would look like on the bridge by placing them on these barriers. And we're doing a lot of things here, but one of them is that we're going to check the formwork and to make sure that the joint concrete flows into those haunch regions on the stringers in particular. We also want to look underneath and make sure that that concrete's not running out, and that the method of attachment to the panels was what we wanted. Of course, we wanted to make sure that that specialized, you know, concrete mix was consolidated in that region. And so, you know, we really pushed these a long ways and right out to the job site. And we were really happy with doing that. At the same time that we're playing around with our mock-up panels, Kiewit's already out on the bridge at this time, saw cutting that bridge and starting to remove deck panels. Our main strategy here was that we just left that saw just about at that bottom mat of reinforcing. We wanted to be really careful we didn't hit that the stringer flanges, and I'll talk about mitigating risk later in the CMGC process, but that was something that we really wanted to be aware. So the contractor just kind of snapped that last half off, and that proved to be a good strategy in this 920 feet of deck removal, which actually went fairly quickly, in my opinion. After the deck is completely removed, our next step is to then place the 96 panels onto the structure. And so you'll see in this video, the first crane was picking a deck panel from a delivery cart, and then you'll see the cart transferring that panel out to the second crane. And then that second crane you'll see as precisely placing those panels in sequence. So as the sequence starts over, I want to point out that Kiewit did a great job of, you'll see the formwork for the curbs already built onto those, and they packaged up a bunch of the steel that would be replaced in the joints. They packaged up the rail that would be then extended on as they placed the next joint after that. So they packaged up a lot of their work safely off site and then brought it out here in a nice clean package on those deck panels. So really went well and very efficient. I also wanted to talk about that crane that's awkwardly out in the middle of the unbuttoned structure without its deck. But we'll see that Kiewit came up with a strategy to make 2 crane trestles. And so in the picture on the left, you'll see that they can lift up. So once their deck panels progresses far enough, they'll actually lift that trestle up, and then you'll see on the right picture where they've swung that around. And then of course they'll place it behind their crane, and then they can walk that crane backwards using that second mat. And so they leapfrog down the bridge in fashion, and it was just a great strategy along with their cart and buggy to really reduce the loads on that structure while we didn't have that deck in place. So we're getting near to being done with our backseat driving, but I did want to bring us right back to that joint. It was a huge part of this. Obviously, I think there was, I'll say 96, 97 of these joints. And here's a completed one with all that steel in there. You'll see the design intent. You can also see the leveling devices. These two would be on the stringers, and then there's of course one on the main girder. You'll see the grout holes. And so a lot of that detail coming to life out on that bridge, and really successful. And of course, I bring back tying that together, the importance of the mock-up and just making sure that when we peeled this deck off and put all these deck panels back on, that we could get them done and in place and finish in that 6-week closure, you know, our promise to the community. And finally, a few shots of the finished structure. Of course, in the left shot, you'll see finished rail, the curb, the cleaned and spot painted steel, as well as seismic seats for new bearings. We actually did a lot more than just the deck panels while they're in there. But of course, then that finished ride surface on the right picture showing the bridge with that 1.5 inch overlay. And so we can't avoid, you know, talking about all the good things and successes there without talking about a few of the challenges that we had. As Stephanie mentioned, we had a short pre-construction time frame. We had about 8 months between kickoff and award, and we had a lot to figure out. One example with that is the road closure decision. It was really a pivotal moment in the pre-construction process to really shift our focus from that one lane at a time, maintaining traffic, to actually needing to close this down. Not only are there design changes, but there's a lot of, you know, we had a huge shift into public input and involvement. And as I mentioned earlier, there's a regional coordination effort. And the reason why, you know, we took on those challenges was safety, both for the public and the contractor. But there are other benefits to that. One of them, you know, as a bridge engineer, that I appreciated was it eliminated that longitudinal joint between adjacent deck panels, you know, because we had that full width panel now that wouldn't have been possible. The formless deck panel joint, you know, we can all see that it was congested. It was a challenge. I think this team met that challenge head on, as I've mentioned numerous times with those mock-ups, and we really did our homework to make sure that when we got out to the job site with those 96 other panels, that, you know, that steel would fit in. And so I think, you know, challenge accepted on that one. The team did awesome. I can't go on without mentioning the shear stud size. We used 1.25 inch shear studs. And I think, to say the least, you know, they made a lot of sense in pre-construction. It helped us reduce the shear stud blockout sizes. And as you remember, I showed all that congestion with the steel and the blockouts and all those things, but they really proved to be more challenging in construction than we first knew. In fact, we had to have those specially fabricated. And then, of course, doing all our weld procedures and trying to bend those over. Challenging is a good word for it, from what I understand. And then Stephanie did mention the COVID in March 2020, which we're all familiar with. But, you know, when we're ordering new bearings for this bridge, we have supply chains, you know, things coming in right during this time from January, you know, into May. And so we're writing, you know, letters of essential work and that type of thing. So as Stephanie said, the team did great, you know, meeting those challenges. Lessons learned. We obviously used the first one. I just mentioned the 1.25 inch shear studs. And so I think I can just simply say, you know, they may have actually been, you know, required for this project. We had some extreme requirements to fit those in and all the steel. But if there are any other options, it's worth trying to figure that out, you know, to get those smaller shear studs in. CMGC proved to be an excellent delivery method for this project. And I think in bridge, I think it's a lesson learned that we think it'd be great for a lot of ABC projects. I think we're new to CMGC, but if you're all more familiar with that, it probably makes a lot of sense why we say that. But it really all boils down to the risk and how to mitigate that. So there's a lot of unknowns for this project going into it, and having that contractor and such a good design engineer all, you know, meeting with us and figuring this problems out, it really allowed us to mitigate that risk. One of the clear examples I have of this is nobody knew what the top of those stringers were going to look like when we peeled that deck off. How much corrosion was there? How much could we accept? And so we were able to talk about all those things and figure out ways to, first of all, mitigate that. And second of all, come up with contingency plans. Well, what if we find, you know, something that we weren't expecting? And so we worked all that out ahead of time. And just a great example, in my memory of that CMGC process, one of many, I think. There's a lot of other inherent risks that I think we avoided just by all working together so closely. Possibly, you know, less documented than that steel stringer solution that we came up with. And then, you know, I can't help but mention innovations really define the end solution. Number one, the mock-up was worth it. As we followed those panels through fabrication of the final mock-up, we really felt that we got our money's worth. For example, the value of ensuring that the joint still had clearance prior to shutting down the highway. You know, all those adjustments that we talked about when we walked those panels from, you know, design, fabrication, and into construction, we really think they paid off. So that mock-up was a big lesson learned for us, I think. The formless joint proved to be a good solution, and it may not be perfect for every bridge, but the team felt that it was the right solution, meeting the design challenges and conditions for this project. So it was, I think, a really positive lesson learned for us on that one. You know, the full width panel fabrication and placement, as we discussed, these panels were 34 feet wide, 6.5 inches thick, nearly, you know, 10 feet in width. To manufacture these in just a few months, deliver them unscathed over 125 miles away, and then place them in an unbuttoned old steel structure so smoothly, I think, you know, I walked away, you know, realizing the potential of our workforce and what we can do. Huge lesson learned. And I can't help but mention the ingenuity that Kiewit had with their cart and buggy system, specifically designed for this, to, you know, to facilitate the transfer of the panels while meeting the structure limitations of the bridge. So, you know, that effort was phenomenal. And that brings us to, are we there yet? Our questions. I do want to just give out a shout to all the people that made this happen. There's, of course, our CMGC partners, HDR and Kiewit, and they were key to pulling this off. But I also wanted to mention all the MDT personnel that were involved, you know, all the way from alternative contracting out to the district construction folks that knew the area that we were going into. You know, they were really the ones that were pulling out all the stops and made this project happen in such a short time. And I have to mention too, we had incredible public involvement consultants, and, you know, just MDT really appreciates, I think, the community of Trout Creek and the surrounding regions for helping us, you know, to work with them to make this project a success. And just, there's a lot of hands in there to make all this work out, and we just have really a lot of appreciation for that. So with that, open it up to questions.
All right. Thank you, Lenci and Stephanie, for a great presentation. So at this point, we are going to turn it to Paul Lyles to moderate the question and answer period. And I think, Paul, we have until 15 minutes after the hour.
Okay, Torrid, thank you. And Lenci and Stephanie, real good. We have a number of questions that came in beforehand. You've covered a lot of that in the presentation. And then we had about 10 questions or so that came in during the presentation. So you haven't seen those. But the first question I wanted to ask, and this came in beforehand, was did the general contractor involved during the was the general contractor involved during the construction phase? And that was Kiewit was in your original phase, and you just want to comment on that?
Yeah, sure, I can speak to that a little bit. So you know, MDT's intent with the CMGC process is to bring on the contractor early during pre-construction to really get that company-specific constructability input in a formal contractual way. And so our goal is to select a contractor through pre-construction and at the end of design agree to a price to construct the final project. And so that's sort of how the process went with Kiewit. They teamed with us for design. We came to agreement on price around the time of contract award, and then they proceeded to build the project.
Okay. Then we had a few questions came in beforehand. There's one that says, does Montana use any stainless steel reinforcement in their bridge decks? And not on this project, what is the main factor for using, what would you do to use stainless steel?
That's a good question. We do use stainless steel occasionally. It is very expensive, and so we tend to reserve it for those situations where we have very high ADT, usually in our more urban areas. So we do look at the longevity and the traffic impacts when we select stainless steel. And like you see in this case, we use the high chromium corrosion resistant steel. We do use that frequently as well.
Okay, that's fine. We do have some questions about the Mmfx steel that came in during the presentation, and that's what you used here. The first one is you used epoxy coated bars in the curb and Mmfx for the rest of the bridge. Was there any reason on that?
Maybe Justin, could you take that one?
You bet. Yeah, so we just, so that railing that went on the bridge is a MASH compliant rail system. And so that has epoxy coated rebar as part of that system. So we just didn't want to change that. So that's why we used a different steel in that curve. Okay, that's interesting. Then there was a question about, is there a difference in cost for the Mmfx steel as opposed to, say, grade 60 rebar?
There is a slight difference. Not significant difference, but there is a difference. But again, when we look at the value gained using corrosion resistant steel, we're usually willing to pay a little bit higher cost for that. Okay, and then another spin on that. Mmfx usually has a higher yield in grade 60. Did y'all take advantage of that, or did you just replace it bar for bar? Justin?
Yeah, I think we did need to take advantage of that for collision loads on the overhang, but in general, the serviceability controlled the deck steel. So, in the intermediate bays, we really didn't need that higher strength. Okay. Then some questions that came in beforehand. What treatments were used for the deck panel joints for long-term durability? And there was a question beforehand about what did you use post-tension? You didn't use any post-tension in the bridge, but did you do anything special with the joints other than just use the high-strength concrete UHPC and let that be it?
Yeah, we use that special. It was just more of a concrete mix that the contractor came up with, locally there to protect that joint. And then with that 1.5-inch overlay, the Mmfx steel, we had less concerns about more protection for that joint, but we did provide a sealer at the end of the project as well.
Okay, one that came in beforehand, can you comment on the original deck connection to the steel girders in the new deck? Was that non-composite, I think? And then your new bridge, you mentioned that you made it composite with the main girders, but for the stringers, you just put studs in there to hold it all together. Is that right?
Mm-hmm.
Okay, so, but the new construction was designed as a composite section? Is that,
yes.
Okay, all right. Okay. Here's a little question that came in beforehand about after construction, is stormwater runoff kept out of the reservoir, or was it just use scuppers to let it drop into the reservoir, into the water?
We just we use scuppers, and it was basically perpetuating what was in the existing bridge for this rehabilitation project.
Okay. Let's see, was 3D modeling used by either the designer or the contractor for the panel rebar detailing?
I can answer. I know at Glacier Precast, they had completely modeled all the steel and their formwork and everything to make all that magic happen for the fabricator. So I can say that they did have 3D there. Dustin, on your side, were you working mostly 2D still? For the design?
We didn't really use 3D for that. We just did it 2D. It was fairly straightforward.
That's fine. How was the crane trestle attached to the existing beams?
That is a good question. Ryan, do you remember any details on that?
I do not remember how they attached it.
I was going to say gravity.
I was thinking probably gravity. So anyway, that's fine. Then there's a question here about what was the maximum aggregate size used for the joint concrete? That's a new question.
I'm going to say 3/8 of an inch, but I'll throw it to Dustin and Ryan. 3/8.
Yeah, it was a 3/8 mix.
Okay. Was there any cross slope built into the panels? You had a picture of the panel earlier.
Yeah, I'll bring that up. It was there we go. So it was 1.19%, and Dustin can add to this, but well, go ahead, Dustin.
Sure. Yeah, I mean, we did look at originally just trying to build that into the overlay, but it made sense to build it into the panel. And then we also looked at trying to make the panel flat across the bottom. But the problem with that is that the panel started getting pretty thick and heavy and hard to manipulate, ship, and handle. And plus, it increased the dead load on the structure significantly. So for this rehab project, we were kind of forced to build that into the precast section.
Okay. There was a question here about the leveling screws. This came in during your presentation. Were the leveling screws used in any way to make sure the tributary load, dead load to the stringers and the girders were controlled? And if so, how was that done?
That's a good question. I think the primary purpose of the leveling devices was mainly so we could, as they might suggest, distribute the weight out among all those members, but also, their primary purpose was just to make sure all the heights were worked out as different deflections and, as that structure rebounded maybe differently. So we wanted to be able to handle any of those differential deflections that we weren't expecting with those leveling devices. But, besides the weight of the panel itself, we were really relying on that that haunch concrete pour to really shore up the remainder of that. Dustin and Ryan, do you have any other insight on that question?
Yeah, they had to kind of limit the amount of torque that they applied to those leveling screws as well, so that they couldn't get a high amount of torque on one leveling bolt versus another one. So specifications kind of controlled like how much different. It was intended to keep the weight distributed evenly between those leveling nuts.
Okay. There's a couple of cost questions that came in, or cost related. Were there any claims from the contractor for the project?
I'm going to say from my Bridge Ivory Tower, no, but of course, Ryan's the professional there.
No, there were no claims on the project.
Okay, that's great.
I think that I would say that demonstrates the value of CMGC and having the contractor on board early. Again, so important.
That's what I was thinking. That was a good comment. And then someone had a cost, unit cost per square foot for the bridge.
I don't know if we have that handy, the unit cost.
You had 10.5 million for the bridge, and I guess you could divide
About
out
1,000 feet long and 34 feet wide. Right.
Okay, it's getting on toward 10 after, and I'm going to turn it over to Jugash and see if we've got any questions that came in during the question and answers that we can pick up. Jugash?
Yeah, thank you, Paul. Yes, a bunch of questions came in. I'm going to start with the first one. Would you recommend number of smaller studs equivalent to larger studs?
Yeah,
Right.
if you can fit those, if the shear stud pockets, and if you're able to fit those larger pockets that you'd need for more of those studs, because there's the clearance requirements around each stud. And so if you go smaller studs with more of them, we found that pocket size grew. And I should hand it over to Dustin because they spent a lot of time working on that. So.
Yeah, it was kind of a tricky scenario, just trying to get, to your point, Lenci, trying to fit all those smaller studs into a stud pocket and then move everything else around that, you know, needed to be in a panel. So at the time, those larger studs seemed like the right option, but yeah, I think we'd probably rethink that again if we had to do it again.
Okay, thank you. Were barrier ratings improved from TL1 to TL6?
I think this was a TL4, Dustin. Yeah.
That was improved to TL4
I
then.
think
It was improved, right? So from the original barrier, I don't know that we had I mean, this was pre 350 design, 1958. So yeah, significant improvement from the original barrier design.
Okay. Did you pick up any live load capacity between composite action and maybe a lighter slab? I think they're talking about any additional live load capacity.
Mm-hmm.
Dustin?
Yeah, we did get a little bit of benefit of making the main girders composite. So yeah, it did help. We were able to widen out the deck just a slight amount as well because of that.
Okay. How was longitudinal profile maintained during deck placement?
Mm-hmm. That's a good question. Ryan, I don't know if you have a answer to illuminate there.
We just basically followed the existing structure and used the leveling devices to keep the panels as even as possible.
Okay.
Relatively flat grade across this bridge, if I'm not mistaken, Dustin. So maintaining that was pretty simple. I think there was probably a survey done before construction, and as those panels were placed, you know, just continuing to survey and make sure that we're matching the existing grade as much as possible.
Okay. Why not
Right.
use MM?
Sorry, I was just going to say that modified concrete overlay at the end gave us a kind of another opportunity to correct that if we did have a significant issue.
Mm-hmm.
Right. The next question is, why not use Mmfx rebars in the few places where epoxy coated rebars were used?
Right, I think like Dustin mentioned earlier, we do have a standard TL4 barrier design that included grade 60 steel. So we wanted to stay with the original intent of that barrier design and didn't include it into the curb because of the difference in the yield strength of the two steel types.
Okay. Thank you. Were shear studs existing or new?
They were
New.
all new. There were no shear studs on the original girders.
Okay. Any tolerance issues in the closure joints?
Something I didn't show in the slides, HR did something very clever, but there's, I think, 2 locations on the bridge where they had a little bit larger gap with longer bars sticking out of those panels. And so that would allow, if we lost or gained, that would allow 2 locations where we could make up for that. Dustin, any extra details?
Nope, you said it perfectly.
Was any maintenance work done on the top flange of the steel girders after deck removal?
Ryan?
Yes, they were cleaned and in some places painted.
Okay. What type of overlay was used, modified concrete or regular concrete?
Dustin?
Yeah, it was a modified concrete overlay.
Okay. I think the last question is, how was continuity maintained in the top longitudinal deck steel? The top mat number 5 bars appear to terminate at the face of the joint, and the tie bars are added to the joint in the field. How is the lap splice developed for this top steel?
Dustin?
Yeah, I mean, it's just developed in the joint. We had additional bars in there and developed it through a lap splice. And you probably noticed those joints were a little bit wider with that custom mix versus a UHPC type joint. But yeah, it was just through conventional reinforcement and lapping it in the joint.
That's all the questions I had. Thank you, everybody. Well done.
All right. Okay. So anyway, thanks a lot for very interesting presentations. And on that note, we are going to end our webinars, and we like to again remind our audience that the conference program for the 2021 virtual ABC International Conference is available. You can go to our website, and if you are thinking that to participate, we will appreciate to register for the conference early, and that will be a great help for us. So on that note, we'd like to end the webinar, and until the next monthly webinar, take care and stay safe.